Welcome to Mathematics for Machine Learning. This is chapter 2.1. Let's start by talking about system of linear equations. So you can model real-world problems as a system of linear equations, or you can formulate a real-world problem as a system of linear equations. And linear algebra provides you with the tools to solve those system of linear equations. Now let's talk about a concrete example of a system of linear equations. This is the example given in the book, so I'll just walk through it. So imagine there is a company that produces n products, so n sub 1, n sub 2, all the way to n sub n, so n products. And imagine this company have R resources, so R sub 1, R sub 2, all the way to R sub m. So n products and m resources. Now suppose that A sub I, j refer to the amount of resource, the amount of ith resource required for making the jth product. So if I have to find out the total amount of resource I required, let's start with the first resource. So the total amount of the first resource that the company will require will be A1 first product into the number of the first product, so let's call this x1, plus A the first resource into required to make the second product, so A sub 1, 2, that refers to the amount of the first resource required to make the second product multiplied by the number of second products, plus A1 sub 3 x3 all the way to A1 sub n x sub n. So this is the total amount of the first resource required by the company to make their products, their end products. And now if the problem I have is, if I have a finite amount of resources, which is going to be true in almost every real world problem, and imagine the amount of resources I have is represented by b sub 1, b sub 2, all the way to b sub m, where bm refers to the amount of mth resource. So as a company, I want to figure out how many products of x1 to xn I should make to make sure that I make the best or the optimal use of the resources. So this is actually equal to solving a system of linear equations, which basically means you have a set of equations and you want to find the solution that satisfies all those equations at the same time. So this would be A1 1 x1 plus A1 2 x2 plus all the way to A1n xn equals b1, because this is the amount of the first resource required to make all the n products. And then I could then now talk about the second resource to make the first product, so that's x1 plus a2 2 x2 plus all the way to a2n xn equals b2. And then I can extend this, and then the last row of this set would be a sub the mth resource first product x1 plus mth resource second product and the number of second products all the way to a sub m n x sub n equals bn. So this is a system of linear equations, and linear algebra will then help us find out what is the optimal number of products, or essentially the values of x1 x2 all the way to xn, that will make the best use of the resources, which is the column on the right hand side, b1 b2 b sub until up to b sub n. Now that you have a better sense of what a system of linear equations is, now the third bit, which will make more sense once we come to the geometric interpretation. In every case, you can have one of three situations. Either you have a unique solution, so it's a one unique solution, or either you have no solution at all, or you have an infinite number of solutions. So those are the only three possibilities that can happen when you have a system of linear equations. And there is a geometric interpretation of system of equations. So let's think of a two-dimensional case, and then you can visualize, well, you can visualize 2 dimension, you can visualize 3 dimension, but you can, the concepts that the intuitive sense that we have for the 2 and the 3 dimension, you can then extend that to n dimensions, and that's the beauty of linear algebra. So let's think in a 2-dimensional space. So imagine you have two equations, x plus y equals 0. Let's plot this. So I'm going to do this on red. So let's call this a y-axis. This is the x-axis. When y is 0, x is also 0. So that's the first point. When x is 1, y is minus 1. So that's the second point. So let's call this minus 1. So that's x plus y equals 0. Now let's think of a different equation. Let's do x minus y equals 2. So this would be, let me draw it in a different color. So let's think of a second equation. Let's plot it in blue. So x plus, well, let's do x minus. So x minus y equals 2. Now in this case, when y is 0, x is 2. Okay, that's 1 point. And when x is 0, y is minus 2. So that could be here, and that's what we'll get. So there is a point where they intersect. So a system of linear equations, geometrically, what this means is basically plotting the individual equations. So x plus y equals 0, x minus y equals 2, and then the point where they intersect, that is that unique solution. I said earlier that you can have one of three possibilities. Either you have a unique solution, which is the case shown here, or you can have a situation where you have no solution at all. So that would be a case where you have parallel lines. So imagine this scenario. So you have maybe one equation that goes like this, and then you have another equation that's going like this. So they are parallel and they will never intersect. So this is a case of no solution. And the third situation is if you have an infinite number of solutions. So that would be a case, imagine a 2D space. Imagine an equation, x minus y equals 0. So that would be a line passing through the origin. And then you have a different equations, perhaps that's 2x minus 2y equals 0. So effectively they are same line superimposed on one another. And because they intersect at infinite number of points, so that's a situation where you have infinite number of solutions. So those are the three cases geometrically. This is infinite case, this is no solution, and then this is a unique solution.